an evolutionary perspective. Thank you, Robin.
Okay, thank you very much. Great pleasure, as Colin said, to be here on this auspicious occasion, the launch of this centre. I should look forward in my retirement, I think, to seeing the fruits of it, because I'm much older than you think. I'm sort of going to tackle the question of the brain and behaviour, as it were, from the opposite end to the story that Colin Blakemore has just given you, in both senses, in the sense that I'm going to look really at the front end, whereas he was sort of gave you the story of, in particular, of vision as his main focus, and also I'm going to really look at the behaviour and talk particularly about, needless to say, social behaviour. Well, I would, if I could get something to move. Okay, so let me introduce, in case you don't know, probably the most famous person in the whole of neuropsychology. He actually founded neuropsychology, I dare say. His name is Phineas Gage, and was a railway construction supervisor, gang manager in the northeast US in the last century, who made a serious mistake when laying an explosive charge of banging this tamper down the hole in the rock where he put the gunpowder a little too vigorously, and the gunpowder duly exploded and drove this whacking great piece. This is the actual tamping iron through his cheek here and up through his eye and up through the top of his head. This is what it looked like. There's, oops, come back. There's the hole where it came out. You can see here reconstructions of the damage it did, particularly up in the frontal lobes up here. And the key to the frontal lobes, really, the frontal lobes are quite interesting, particularly in terms of humans, because it's beginning to look increasingly like some of the core areas right up here in the frontal pole, as it were, are unique to anthropoid primates. And they allow anthropoid primates to do stuff at a relatively simple cognitive level that no other species can do. This is essentially has been the argument that Dick Passington has laid out to explain why primates are so good compared to other species at things like one-trial learning, for example. So they can make inferences on the basis of what they see. It's almost as though all other species are kind of inductive scientists, accumulating in the old associative learning style of psychology, accumulating information and drawing generalizations from that. What primates seem to be able to do, particularly based on these areas right up in here, is to make leaps of inference off the back of that. And that allows them to do things like run 2 videotapes of possible futures. If I do this, that'll happen. If I do something else will happen. And see what the options are behaviorally. So that's at the sort of very basic cognitive level, appears to be very important. But the real function that differentiates, particularly in primates, I think, the role of the frontal lobes in particular, although not exclusively the frontal lobes, really is the social world. So there's been a suggestion over the years that things like the internet are going to increase your social world to an absolutely unlimited extent, and everybody knows people who has 5,000 friends on Facebook. Well, this is the distribution of number of friends on Facebook for about 1 million Facebook users. It's not my data, but thanks very much if you contributed to it. And you'll see this very long tail out here to the right. Indeed, there are some people that have the full 5,000. Most of those are using Facebook for professional purposes. The majority of people have somewhere between about 150 and 250 friends on Facebook only. People don't have unlimited number of friends. And the reason for that is the constraints on the number of people that you can have relationships with that is imposed by basically our psychology and ultimately the brain. And the sort of background to that is this story, the so-called social brain hypothesis, proposed many years ago by Dick Fern and Andy Whiten up in St Andrews, that the reason primates have much bigger brains than all other species of mammals is the complexity of their social systems. And here are essentially data that point to that. If you plot something like, mean group size as a measure of social complexity, you can put quite a lot of different behavioural measures in there, and plotted against some measure of brain size. This is just neocortex ratio, the ratio of the neocortex to the rest of the brain. That's simply because that's the only kind of data that was available. Could we partition the neocortex down? And when we originally did this a very long time ago, the neocortex divided by the rest of the brain to take out the scaling effects of brain size in different species. Then what you get are these sort of tram lines, essentially, of correlations between these two variables. But there are clear grade differences. There turn out to be actually 4 separate grades in here, which are really quite tight, with the 8s lying out here. Since we're 8s, if you plug us in, we know where we lie on this from that same data set. It's there, and that gives you the infamous number, now known as Dunbar's number, of 150. Ironically, it's Kristen Dunbar's number on Facebook, of all places. Well-known emporium of science. Anyway, here's a prediction as to what people actually have as the natural social group size. We can give you lots and lots of data of various kinds, casual data of this kind, from various historical and contemporary sources, or real data. These are ethnographic censuses from ethnographic societies, small-scale hunter-gatherer and horticultural societies. Here's one of our databases for, so this is looking at the world top-down, if you like, to see how people are distributed in space. And here, this critical group in here sits very nicely around the predicted value of 150 here. This is our attempt to look bottom-up at people's individual social networks, the picture of their social world, as it were, using, in this case, the number of recipients in houses to which they're sending Christmas cards. And there's a lot of variance in this, which is interesting. I'll come back to that. But there's quite a strong peak here, and there's a very nice mean value at, where are we, 154, almost exactly bang on. These data I kind of like because it's a reminder, since some of them are about management structures and research, the size of research subdisciplines, it's always a good reminder for vice chancellors and deans how big they should aim at, or how not so big they should aim at. In some cases, we're in the current fashion for making ever bigger units. It looks like there are only certain kinds of unit sizes that we can cope with effectively, is the message. Anyway, so here's some data that this 150 value has some reality. It is a mean. But the question we have to ask, particularly in the context of today, I think, is how we and other primates organise our social relationships. What's the kind of mechanisms involved beneath this gross correlation that's determining or placing this limit on the number of relationships that we can actually handle, and presumably the story is going to be the same for the smaller groups of primates as it is for us. Well, our view that we've come to with the way primates create social relationships is it's really a two-process mechanism. There are two completely separate processes which sort of come together to produce the quality of relationships of which these numerical values then emerge. So the numerical values are really emergent properties, really, of what's going on at a much deeper, more personal level in the individual and in the individual's brain. And those two components consist of a very intense emotional component, which is triggered by grooming, this kind of stuff, which primates do a lot of. And I'll show you in a minute. This is driven primarily by endorphins. So here's a neuroendocrine mechanism underpinning it, and we think is this sets up a sort of psychopharmacological platform, as it were, in the brain, of which the second component, which is the cognitive component, is then launched. So this provides some kind of mechanism which allows individuals to get together, of which they can then build a relationship of trust and obligation and reciprocity, which is what social relationships seem to be all about. And I'll just sort of talk you briefly through each of these, give you some sense of what's involved, really. Okay, so grooming takes up an enormous amount of time for some primate species. These are the average amounts of grooming time devoted to, total amount of daytime devoted to grooming for a species. So these are species averages. Here's social time as a percentage of the day, and here's group size. And in general, there is a very good and significant relationship between those two, except that it kind of tails off eventually at somewhere around about 20% of total daytime. That seems to be the upper limit to which any species invests in this kind of activity. And that's simply a consequence of the fact they have other stuff to do, which fills up the rest of the time. But this part seems to be extremely robust, with essentially a linear relationship between the size of the group and the amount of social time. What's important to remember, though, or is worth pointing out, that as you increase group size here and you're increasing grooming time, you're not actually, in any of these species, grooming more individuals. What you're doing with all this extra grooming time is investing more and more of it disproportionately in your core inner little group of key friendships, if you like, your key coalition that supports you. And what that coalition does, and this is what gives the complexities of primate societies, is you're using these grooming-based coalitions as protection against the costs and the stresses of being in very large groups. And so they're really handling two separate problems simultaneously. One is rather weak relationships with these guys on the outer periphery of the group, as it were, and very intense relationships with their inner core key friends, their coalition partners. And here's some of the nice evidence from Barry Cavern's lab many years ago, showing that endorphins are key to this issue. This is a particularly nice experiment because what he does is he's given very, very small doses of morphine, so small you couldn't detect them in serum, so subclinical doses, to monkeys with a saline control, a neutral salt solution here as a control. And animals that have had the morphine dose, as it were, lose all interest in social grooming. So this is, you can plot a number of measures here of social grooming interest. This is just the number of animals they groomed with. And there is a sort of big difference here. The morphine dose animals just groom less. Morphine is, you want to remember the endorphins, particularly the beta endorphins, which seem to be the operative ones in this context, are like or members of the opioid family. So morphine is a particularly good mimic for that. And in fact, this has been used to explain why drug addicts opiate drug addicts lose interest in the social world, stop having relationships and so on. Basically, they're getting their kick, their opioid social kick, as it were, artificially, and they don't need human interaction to give it to them. But this is the neat component. What he's done is the reverse experiment giving naltrexone, which is an opiate blocker, which locks onto the receptor sites for beta endorphins, blocks them up, but is completely neutral in what its effect that it has on the brain, other than making you feel a bit rough. And you can see that by comparison with the saline controls, these animals are desperately trying to get more and more grooming. They're really desperate to get it because they're not getting the kick. They're doing the grooming, but they're not getting the kick that makes them feel contented and good, as they normally would do. Okay, and this is just to show you the same effect in humans. This is pilots from a PET scanning study we've been running with colleagues in Helsinki, showing the brain regions that are particularly responsive to beta endorphins firing up in response to very, very light stroking. This is the McGlone effect, I like to call it. This is well, what we suspect anyway, this is his infamous afferent C fiber tracts responding to very light touch and very light touch only, firing up the endorphin system. This is grooming, because that's what grooming is. It's not a lot of heavy massage, it's a lot of quiet stroking of the fur. That's what the monkeys are mostly doing if they're doing this stuff. So here's evidence in humans of exactly the same mechanism involved. Okay, so that's the sort of the basics of the neuroendocrinology side of it, as it were. The cognitive side of this component, I'll come back to the other half of that in a second. The cognitive side of that is really has to do with mentalizing. Pretty much everybody, I think, in this kind of area recognizes that there is a class of cognition which they generally refer to as social cognition, for want of anything better, which is peculiar to these kind of intense social interactions which we and maybe other species engage in. But the problem is we don't really know what it is. Alan Leslie, 20 odd years ago, said this stuff is really very interesting as theory of mind. We know a lot about it, we know a lot about its natural history, but we have no idea what it actually is, what's going on in the brain to produce it. So the sort of nice thing about this is, though, that mentalizing or theory of mind forms part of a natural continuum, a natural hierarchy of complexity, which forms in effect a linear scale, and this sort of really is spun off the back of the original conception of this in philosophy of mind. So Jack hears in first order intentionality, he has a belief about the world of some sort. In effect, he knows the state of his own mind. Jill hears in second order, she believes that Jack believes that something is the case. This is classic theory of mind, second order intentionality. Children go through this at about the age of 5. By 5 to 6, they're absolutely rock perfect on it. To get this, probably the only other species that can do this are great apes, and they're okay, but not as good as 5-year-old kids. The thing is, adults can do much better than that. This is this sort of reflexive hierarchy going out here. We can handle much better, several more orders beyond that as normal adults. And in fact, it turns out that fifth order intentionality, which is being able to handle a statement that looks a bit like that, or a thought that looks a bit like that, is the average for normal adult humans. And that in certain kinds of diseases, for example, or clinical conditions, for example, paranoid schizophrenia, bipolar disorder, people lose these higher levels of intentionality. And that may account for some of the, particularly in the case of paranoids, misunderstandings that they produce behaviors. Okay, here one of our first data, in fact our very first data, there's our second data set actually, I think, trying to look at what the natural limits are, done some years ago now. It's just plotting, we called it the level of failure here, but actually it's the highest level at which you can pass these kind of vignette tasks, multi-level false belief tasks. And these are at the various levels. I'm a bit skeptical about these up here, but we've replicated this pattern and this effect at fifth order as being the sort of average norm several times now, so they're pretty robust. But the interesting thing is not just that the norm is about fifth order, which is considerably more than any other species, by 3 orders, as it were, any other species the primate can do, but there's a lot of individual variation involved in that. And that may come about partly for the reasons of shared genetics, as Colin showed you in the twin study maybe, but also partly through learning experiences. So what very likely affects performance and development of these kind of mentalizing competences is your experience through childhood and adolescence socially. But what we can do here is, so here in effect we've got some software performance, if you like. We can correlate that with some behavioural output, the size, the number of friends you have, and when you do that you get a lot of mess, but some very nice correlations. Again, this has all been repeated several times with different populations. This is a nice significant correlation between the number of friends you've had and how good you are on these tasks. So this is in effect a prediction, a relationship between some software, some cognition, and some behaviour, some output. Lots of variance in that. We know what produces a lot of that variance. Some of it's due to sex differences, a very strong gender effect. Women tend to be much better on these kinds of tasks than men. No surprise to half the audience. There are big personality effects. So there's an strong extroversion effect. There's a strong neuroticism dimension effect as well. But what this raises is the possibility here that we've got some sort of software, some output. What about the hardware? A sort of 3-way correlation between the two. The answer is yes. And I should have put this one in earlier. It's just to illustrate This is an fMRI study combined with the reaction time study to show how hard it is, how much harder it is for the brain to do these kinds of mentalizing tasks than to do normal factual recounting tasks. So basically they're reading little vignettes, little stories about people doing things with each other and thinking things about each other, and they've got a set of questions which are purely factual, and don't involve belief states, don't involve mentalizing, and a set of questions that involve mentalizing. And when you look at these, you get this rather striking effect that as you go up in levels, it gets harder and harder and harder, reaction times slow down. Once you get sort of to the higher levels, they really start to separate out. Mentalizing tasks become much harder for the brain to cope with, and here's a bunch of fMRI results showing exactly that particularly in the core theory of mind circuit and in the frontal lobe, and particularly on the temporal lobe here, these units are working differentially harder neurally when they're dealing with mentalizing tasks than when they're dealing with the matched factual tasks. So that's what the colours are, the differences between the two tasks, the yellow and red are the areas that are working disproportionately hard under mentalizing. Okay. What we can then show is that there's a very nice correlation between the size of those areas in the theory of mind circuit, the standard theory of mind circuit, but particularly in the frontal lobe, up in the ventromedial prefrontal cortex up here. The size of that, both on a very large scale structural MRI analysis, but also on a voxel-based morphometry, very fine-grained analysis, between the size of these units, and particularly in the frontal lobe, and your competence on mentalizing tasks, and in turn the number of friends that you list as being close friends, as it were. And here's some other data from other studies showing this, basically confirming what we found. This was a bunch of stuff done down at the ICN in London, using the number of essentially the number of Facebook friends you had. So we're looking at the inner core of close friends, as it were. Here they just had everybody the size of your Facebook page, looking at, again, picking up some of these core, same core areas in the frontal lobe and temporal lobe. And here, and this I think is absolutely superb, exactly the same effect in the cat monkeys. So this is correlation between the size of these key areas, here we are again right up in the prefrontal cortex being one of those, and the size of group that an animal is housed in and can cope with. So here's very nice evidence, I think, showing that the social brain effect works both ways. It works as a comparative effect between species. It also works bottom up at the individual level in terms of individual differences. Okay, we can also show, at least from the stereological analysis we did, that there is a causal sequence here which works this way. That if you do a path analysis looking at the various alternative ways that these 4 bits or 2 bits of the brain, the mentalizing competences and network size might be linked up, this is actually the only one that causally comes out as significant. So the size of this bit of the brain determines your mentalizing competences, and your mentalizing competences determines network size. Okay, so let's go back to the grooming bit. The key to that really is time investment. And here's that same relationship again. Maximum about 20%. We plug what humans ought to do if we were grooming, making our relationships by grooming. Here we are at 150. If we just extrapolate the line through and predict what we get by that, it would be about 45% of time spent grooming. Aside from the fact you'd be absolutely off your rocker with opiates. Probably any academics have so much time in real life they can spend that amount of time. Sorry, Vice Chancellor. Not your staff. If you plot what people actually do, It looks like this. This is the average for 7 activity budget studies for human populations from all over the world, from a population in Dundee to hill farmers in the Himalayas and horticulturists in New Guinea. Turns out that we spend exactly 20% of our time engaged in social interaction. So it looks like we use the same limiting maximum that other primates do, but somehow we use it more efficiently to bridge that gap. And the way we think now that this is done, and I'll illustrate this in terms of the amount of grooming time that would have been expected for all our fossil ancestors going back to the Australopithecines 3 or 4 million years ago here. So this is just taking the cranial volumes of the fossils, mapping them through, interpolating them through the regression equations to get brain size, out of that to get neocortex size, out of that, using that to get group size, and then using that to predict grooming time. You'd see a picture that looks like this. Here's the 20% Australopithecines just being jobbing apes, like they're really turning out to be. Only with the appearance of the genus Homo do you get this sort of jump up, and away we go. So somehow at this point we're doing something different. And what we think we've probably done is introduce successively these 3 activities to bridge that gap. And they probably came in at these sort of time scales here, with laughter here being much the earliest. So we think that's the earliest because we shared that with great apes, all great apes and humans. We've changed the format slightly to make it much more exhausting. And here's the key to all of these. They're physically tiring activities. These are really the rituals of religion rather than religion itself. These all involve stresses on the body, and it's stresses on the body that give these endorphin kicks. And that what we've done effectively is found other ways of producing grooming with many other people at the same time. It's the big problem for grooming, the way primates and we ourselves don't do it, is it's a one-on-one activity. Just to show you that these really do produce an endorphin hit. These are the collection of studies we've done looking at musical performance and at laughter, and they're done using a pain assay for endorphins. Endorphins are extremely difficult to pick up because they don't cross the blood-brain barrier, unlike many of the other neuropeptides. And therefore, a lot of the pain research stuff has been done on pain assays, and we know these tie up very well. Pain tolerance ties up very well with endorphin production in the brain from the pain world. So we're using the increase in pain threshold across some activity here as an assay for endorphin activation in the brain, and we're running a series of experiments where the subjects do something musically against a control where they don't. So most of these are in some form of active musical participation. This is a drumming circle compared with, this one was done here in Liverpool. I think this is the staff in the HMV record shop in the city centre. So they're listening to music all day, but not doing it. These guys are a drumming circle actively doing it. This is a charismatic religious service, so lots of singing and upper body movement, dancing. This is, you'll draw your own conclusions here, an Anglican prayer meeting with no hymn singing of any kind. And you can see the 0 point here, if there's no change in pain threshold, no endorphin activation, they should all lie on here, as all the controls rather nicely do. But when you've got these activities, this is performing music as opposed to listening to music in various kinds of ways, you get this upsurge in endorphin activation. Exactly the same story here with laughter. These were, I think we did 6 separate experiments in the end. Most of them were done in the lab, except this one, which we did live up on the Edinburgh Fringe Festival. So this lot here were watching stand-up comedy at the Fringe, this lot were watching little dramas. And what we did for the rest, though, was to get them to watch a video of somebody like Michael McIntyre or Mr. Bean or whoever, stand-up comedy that makes people laugh, and they would run it against a control. And I must say, and I do apologise to those of you who engage in this activity, but by far the best control we found, because it never produced any laughs at all, with golfing instructional videos. But you can see again the strength of the effect. By and large, the controls are all at or below 0. The music, comedy with people laughing, actively laughing, they're all above. But anyway, there's always a significant difference between the two conditions. But this raises an interesting question in terms of the nature of our sociality, really. If the whole key to sociality is simply an endorphin kick and feeling this sort of lightheadedness and highness that you get from it, then that's easy. We can fix that. Society will be easy. You just send people off down to the gym every day and away they go. And you've seen people do this as you walk past the gym, no doubt. They're banging away. The big problem, though, and I'm sure they're getting a little endorphin high out of it, but the big problem is that socially that actually doesn't seem to work very well. What seems to be particularly important in social terms, and the reason these other activities work, is they're socially integrated and highly synchronized. So just doing it on your own with your earphones on, listening to whatever your favorite music is, isn't giving you this massive endorphin surge which seems to create large-scale human sociality. Our evidence for that, we've done more stuff on dance since then, but this is our original study, our first go at it. And on the rowing, 8th rowing cruise, this is the Oxford, for those of you who really care, that's Colin and me, the Oxford-Cambridge boats racing against each other. This is 2007. The neat thing about this is it's not about, from our point of view, it's not about physical strength. These guys are all professionals, rowers, they're all massive, except for the little guys in the back. And they can row, from here to kingdom come. The key to success is synchrony. It's how long they can keep their oars in perfect synchrony, because once you lose synchrony in these boats, you lose power dramatically. Now, this is less than a quarter of the way up the course on the 2007 race. Oxford lost it. They have already lost it here. They're looking like they're neck and neck, but they've already lost it because the oars are now already out of synchrony. Something went radically wrong. Look where his, if you can see it, oar is here, the one behind stroke here, number 7. His oar is flat. Theirs are all half feathered. They've already lost the race because they're not in sync. So this gives us a neat little experimental situation which is very specific to the role of synchronized behavior in social contexts. And what we did was we got them from their morning workout on the rowing machines. They did 45 minutes of this at some ungodly hour in the morning. We made them do a pain test before and afterwards as normal. And we had them do it. The 2 crews, the first boat and the second boat, on 2 successive series of sessions on their own. And you can see this nice little uplift in endorphin production as a result of just doing the physical exercise. And then following that on the next day in each case, so this is all, which I think is 12 of the 16 crew in each case. It's 12 of them there, it's 12 repeating it the following week. We then got them to row as virtual boats, because you can link these up as virtual boats through the computer. So they're rowing in synchrony. When they do that, just look at the uplift they get. Now, that's not because they're rowing harder, because we know that for 2 reasons. One, we can measure the output on here, and it's absolutely constant across all 4 things, but also they're professional rowers, and we said, okay, row at this power output and keep it going over these 4 sessions, and they did. This is purely the effect of social synchrony. They know they're in a boat together, and even though they're only doing it in a virtual boat. So there's something very peculiar about the way the brain produces these social effects as a result of these kind of synchronized behavioral things. I think this is the key to religious rituals, which are highly synchronized. It's the key to dancing and to music performance. It's the key to laughter, which is an incredibly synchronized activity, much more so than you might think. Thank you very much.